So we were going to show that the limit, or we showed last time, the limit as n goes to infinity of 3n over n plus 2. So this is equal to 3. Or we would say converges to 3. The way we did it last class was by doing this whole, like finding capital N in terms of epsilon and saying as long as we were bigger than that number, then you're far enough out, then you're close enough to 3. But there's another way to show that a sequence converges, like to actually kind of prove it converges, other than just like we would, if I was doing this limit just as a limit, be like it's 3 because you've got n to the first tier and n to the first tier, and the quotient of the leading coefficients is just 3 over 1. But a more rigorous kind of proof in quotes, of this fact would be to either do a delta epsilon sort of thing or an n epsilon sort of thing, or this other thing. So another way to show that the sequence converges is to prove two things. Thing one, we're going to show that the sequence a sub n equal to 3n over n plus 2 is increasing, or actually more generally non-decreasing. And there's a couple ways to show sequences are increasing or decreasing, but we're looking for increase right now. But the very, very general idea is we just want to show, if we're trying to show it's increasing, we're trying to show that the next term, a sub n plus 1, is bigger than the previous term, a sub n. That is very generally what we're doing. Next term is bigger than the previous term. Or if you want to show it's decreasing, you show a sub n plus 1 is smaller than a sub n. All right, well, so that's going to mean, I'm just going to literally write the things here. So I'm going to have 3 times n plus 1 over n plus 1 plus 2. Is that bigger than 3 times n over n plus 2? Maybe. I'm going to check by doing some cross multiplying. So I'm going to have 3, I'm going to multiply that with the 3n plus 1. So I'm going to have 3n plus 3. I'm going to multiply it by n plus 2. And I'm asking still, is that bigger than 3n times this denominator here is n plus 3? Okay, let's multiply it out. I'm going to have a 3n squared. I'm going to have a 6n plus 3n, which is 9n plus 6, bigger than 3n squared plus 9n. Oh, I forgot the n here, sorry. And yeah, those cancel, and it's certainly true that 6 is bigger than 0. So that checks out. This sequence is increasing for all n's that are positive. Certainly, right, if we're letting n go to infinity, it's definitely increasing where we need it to be. One thing to note here is that when you cross multiply both sides by the denominators here, if you cross multiply across an inequality, you have to be careful about multiplying both sides by a negative, but that wasn't an issue here because we know that n plus 2 and n plus 1 plus 2 are both positive because n is going to infinity. So it's not something we have to worry about in this case, but something you want to think about in general if you're dealing with inequalities. So we showed the first thing. We did it. It is increasing. And then we have to show something else. So what we're saying here is all the terms are getting bigger and bigger and bigger and bigger and bigger. That doesn't mean they converge yet. They could go bigger and bigger all the way to infinity. What we also need to show is we need to show that the sequence is also bounded. Specifically, since it's increasing, we only really have to show that it's bounded above. We know it's bounded below by take your pick. You could say it's bounded below by 0. There are other numbers it would also be bounded below by, but it's certainly bounded below by 0. And it can be bounded by above. There's a lot of different choices. We often like to try to choose the least upper bound just because that feels the best. But really, you can pick any number you think. So if I start looking at terms here, if I start writing out terms, if n equals 1, I get 3 over 3, which is 1. And if n equals 2, I get 6 over 4, and then, so on and so on. 9 over 5, et cetera, et cetera, et cetera. Well, I'm going to just pick something. I'm not going to pick the least upper bound. I'm going to pick 4. Because I know that if the limit is 3, this thing, it looks like it's getting larger and larger and larger, but it's always under 3. I could probably pick 3, but I'm gonna pick 4. So bounded above by 4. Let's check. Well, what I'm really saying is that my sequence, no matter what n is, 3n over n plus 2 is less than 4. True? Probably. Let's cross multiply, or not cross multiply, let's multiply both sides by n plus 2. So is 3n less than 4 times n plus 2? Is 3n less than 4n plus 8? Yeah, I think it is, because I'm going to just subtract 3n and say, yeah, n plus 8 is definitely bigger than 0. And that checks out. Because again, n is starting at 1 and getting larger and larger and larger. So here's what we've done. We have shown that the sequence is increasing. We've also shown that the sequence is bounded. So it's getting larger and larger and larger and larger and larger, but it can't ever get larger than 4, which I just picked, right? You could have picked anything. And there's a theorem that says if a sequence is bounded and it's either generally monotonic, meaning always getting bigger or always getting smaller, then it has to converge. So that's a theorem. Hopefully your professors maybe mentioned, I don't know, maybe not, but that's a theorem. The theorem is if the sequence an is bounded and either strictly increasing or strictly decreasing, which is we generally say monotonic, then it converges or is convergent. So that's one way to show a sequence converges. And we definitely come back to this theorem when we talk about the convergence of series. So that's probably why we're talking about it now, because it's going to be useful later on. I'm not going to prove this theorem, but we could if we wanted to. We're going to do more examples. I should also pause for a second. You're welcome to ask questions, ask for clarification, whatever. If I'm saying something that doesn't make a whole lot of sense because I missed something, please, please, please ask me to clarify. I'm happy to clarify. I'm just trying to show you as much stuff as I can. Jeremy.
Does it have to be like monotonically decreasing?
Yes. No, it has to be one or the other.
But it could be.
Totally, yeah, it could. You could totally have one that was decreasing, and it would definitely, as long as it was bounded, it would also be convergent. For example, sure, the sequence a sub n equal to, I could write it like that. Let me think for a second. I want that to be decreasing, so I want that. Sure, let's say we had something like, brain 5 plus 1, but I want it to be, yeah. Let's say we had something, I'm gonna make it kind of silly, 5n plus 2 over n. I feel like that's the same thing. No, that's not quite the same. Yeah. Cool. Caleb, when you have a chat a second, please do fill out the attendance form. So let's do the same thing real quick. Let's show that this converges. Well, what do we think this converges to? In fact, write it down. Just tell me, or don't tell me. Write down for yourself what this limit is. I'll give you 5 seconds. I know I'm not clever, but the limit is 5, and we know it's 5. Really, from 21. I mean, you could use L'Hopital's rule if you really wanted to, but that's kind of what's the phrase? Using a nuclear warhead to kill an ant. I think there's some phrase about like using too much power when you don't need it. L'Hopital's rule is way overpowered for this. You don't need it here. You can just see that you have a polynomial over another polynomial. The degrees are the same, so the limit's going to be the quotient of those leading coefficients. 5 over 1 is 5. But now we want to actually show it. Show/prove it. Okay, great. So we're going to do the two things. We're going to show that it's bounded, and we're going to show that it is monotonic, meaning it's either increasing or decreasing. I don't actually know if it's increasing or decreasing yet. I'm going to write down some terms. So if I start writing down some terms, a sub 1 is going to equal 5 plus 2 over 5 over 1. My goodness, James, come on. And a sub 2 is going to be, well, I'm just adding 5 to the top and 1 to the bottom, so it's going to be 12 over 2. That got smaller, right? It's 6. And then a sub 3 is going to be Add 5 to the top again, 17 over 3. A little bit smaller. A sub 4 is going to be 22 over 4. A little bit smaller. I'm thinking it's probably decreasing. Now, I should say, just because you've looked at the first 4 terms doesn't mean you really know what's going on. You might have an idea that this is probably decreasing, but we don't actually know that for sure until we've shown it. So we think, and we're going to try and show that this is decreasing. So I want to show that the next term, a sub n plus 1, is smaller than the previous term, a sub n. That's what I want. Okay, well then I'm just going to literally write the thing. So a sub n plus, you could do a sub n plus 1 less than a sub n. You could do a sub n less than a sub n minus 1, as long as you're just saying the next thing is less than the previous thing. All right, so here it's going to be, let's see, a sub n plus 1, it's 5 times n plus 1 plus 2 over n plus 1. And is that less than 5 times n plus 2 over n? Well, I could do the same sort of thing I did before, but I could also be a little bit more clever. I could instead observe that I could break each of these fractions up into 2 fractions, because that's how I came up with this. If I write this, I can write this as 5 times n plus 1 over n plus 1 plus 2 over n plus 1. And I can write this as 5n over n plus 2 over n. And then things cancel. This is really just 5 plus 2 over n plus 1. And this is just 5 plus 2 over n. And then the 5s, we can just subtract from both sides. And let me ask, is 2 over n plus 1 less than 2 over n? For sure, the thing with the bigger denominator is the smaller thing. So this is decreasing for any positive n, which is all we care about because we're not thinking about n being negative. Okay, is it bounded? So since we know the sequence is decreasing, or since we showed the sequence is decreasing, we only really need to worry about it being bounded above or below. Right, if it's getting smaller, we have to make sure that it doesn't get negatively infinitely small. So we have to check out below. So is it bounded below? Yeah, I can see a bound. I'm going to pick 5, which is the limit, right? It's certainly, the limit is 5. And not that the limit is always going to be an upper or a lower bound, depending on which way you're going, but it often is. So definitely 5 is a lower bound, and it is the greatest lower bound. Proving that's a little more work. We don't need to prove that, but let's check. Sure. 5n plus 2 over n is definitely always bigger than 5. I'm just going to rewrite it as 5 plus 2 over n, and yeah, that's bigger than 5. That checks out. Great, we did it. We proved that this thing must be convergent. I will point out, we didn't actually prove what it must converge to. We just said it's bounded and it's monotonic, that means it converges. But that doesn't actually prove what it converges to. Yeah, Dylan. Either way, yeah. So to show something's decreasing or increasing, right. So if I want to show decreasing, I'm just trying to show here, these are the words I'm saying in my head. I'm trying to show that the next term is lesser than the previous term, right? Because I'm trying to show that things are getting smaller. And there's like 3 ways you could write. I mean, there's really more than 3, but there's 2 typical ways of writing this. You could either say the next term a sub n plus 1 is less than the previous term a sub n, or you could even do the next term a sub n is less than the previous term a sub n minus 1. And then to contrast that, if you want to show increasing, you're just going the other way. Increasing, you're showing that the next term is bigger than the previous term. So we want to show that a sub n plus 1 is bigger than a sub n, or if you prefer, a sub n is bigger than a sub n minus 1. That's the usual way of going about it. Yeah, cool. let's look at another example of a sequence, a recursively defined sequence. Recursively defined sequences are kind of funny because you essentially have to know at least one previous term to get the next one. Let's look at this example. Let's say we have a sub n plus 1 equal to the square root of 6 plus a sub n. And we're going to start with, you can't just have the recursively defined sequence, you also have to have a starting place. So we're going to start with a sub 1 equal to the square root of 6. I guess I could have started even further back and said, I'm going to start with a sub 0 equal to 0. Could have done that if you really wanted to. Okay, so does this converge? Good question. Let's talk about the two kind of ways you would approach this question. One way is to say, well, I think it converges. I think this limit exists. So I think yes. And so what that means to me is that I think the limit as n goes to infinity of a sub n is going to equal some real finite number, which we often call capital L. But if the limit actually exists, that means it's the limit of either this or this, right? They're the same thing. So I could really say this is going to be the same as the limit as n goes to infinity of the square root of 6 plus a sub n. So it should be the same, right? This thing here and this thing here should go to the same place if that limit actually exists. But that means if I move the limit inside the square root, this should actually end up equaling the square root of 6 plus the limit as n goes to infinity of a sub n, which is going to be the square root of 6 plus the limit. So what we're going to do is we're just going to replace a sub n and a sub n plus 1 with the same variable L and then solve for L. It's kind of weird, but it works. So we're going to say that L has to equal the square root of 6 plus L. And then we're going to solve. We're going to square both sides. Okay, L squared equals 6 plus L. We're going to bring everything to the left. L squared minus L minus 6 equals 0. We're going to factor. We're going to factor L minus 3 times L plus 2 equals 0. So what are our possible solutions here? L equal to 3 or L equal to -2. One of those is not, maybe, so I should say at least one of those is not right. Maybe both of them are not right. You can get possible things the series converges to, but actually are both wrong. Here though, -2 is definitely not right, because if we keep plugging in, we start plugging in root 6 and then keep plugging in more and more numbers, you're just going to get, I think, larger and larger and larger. It looks like 3 is probably what it converges to. How would we show it? Yeah. Well, we could do the same sort of thing. So I'm a fan of this idea of showing things converge by showing the two things. Can we show that a sub n plus 1 equal to the square root of 6 plus a sub n, where a sub 1 equals root 6? Can we show that this is 1 monotonic and 2 bounded? Maybe. It's kind of hard, especially when they're recursive. Showing both parts are kind of difficult. But let's check and see. So it's probably increasing. Let's think about it. A sub 1 is root 6. And a sub 2 is the square root of 6 plus the square root of 6, which is certainly bigger. A sub 3, just to write and I guess I could write actual values here. I have written these down in the past. This is approximately 2.91. A sub 3 is the square root of 6 plus the square root of 6 plus the square root of 6, which is approximately 2.98. But I'm probably doing more writing than I need to be, because if I'm just trying to show it's monotonic and I think it's increasing, I'm going to try and show that the next term is bigger than the previous term. All right, well, that's actually not too terrible. Ooh, is it too terrible? I don't know. It might be kind of terrible. Because I know that a sub n plus 1 is the square root of 6 plus a sub n. Is that bigger than a sub n? Maybe. I guess it depends on where you start. If I'm going to try and solve this inequality, I'm going to do the same thing I did before. I'm just going to end up getting 3 and -2 again. Let me show you what I mean. I'm going to square both sides. As long as both sides are positive, it's totally fine to square both sides. Not breaking any rules. Actually, that's not entirely true. I should take that back first. I have to think for a second. If something's bigger than something else, is the square of it bigger than the square of the other thing? Is that true? That's a good question. If a is bigger than b, is a squared bigger than b squared? Yeah. Think about the graphing. I get if they're yes, if they're both positive. I'm thinking about the graph of y equals x squared. Right? If a is larger than b, then certainly a squared is larger than b squared. That tracks. But it's good to think about that, right? Like I was just kind of, yeah, of course it works, but like you really have to think about it for a second, like, does that really work? Yeah, it works. So then we square both sides. And we're going to end up with the same thing we had before. Right? We're going to get an squared minus an minus 6 less than 0. So we have an minus 3 times an plus 2 less than 0. So we either need an to be larger than 3 or an to be less than -2. Nah, sorry, that's the wrong part. Apologies, I totally blew it. I didn't show my work. I was just kind of be like, oh yeah, I know that's fact. If an is bigger than 3, let's think about that for a second. If an was 4 times 6 is definitely not negative. I was getting the end parts when I really wanted the middle parts. So what I really want is neither of these things. This is going to be true as long as my a sub n is between 3 and -2, which is good because that's where I'm starting. Right? I started with a sub n equal to the square root of 6, which is certainly less than 3. Cool. Bounded. I should clarify here just to make sure I'm being clear. What we're doing here is we're saying we want this to be true. We want this to be, we think, increasing. And we're showing here that, okay, well, this is true as long as you have met this criteria. So this sequence is increasing for any a sub n that starts between -2 and 3. You could have started at 1 instead. And if you started at 1, then your next one would be the square root of 7. And then you'd have the square root of 6, right? It would be some other sequence, but you would still end up having the same sort of quality. Bounded. Well, what do we think a bound probably is? Yeah, it certainly seems like, looking at the evidence here, that this thing is probably bounded above by 3. So we think 3 is probably an upper bound. But it's kind of funky because you're just kind of saying, well, okay, great. Is the square root of 6 plus this going to be less than 3? It's kind of weird because it's defined recursively. So this whole bounded thing is a tougher nut to crack when you have a recursively defined sequence. Yeah, I'm trying to remember how you're supposed to actually do this, and I am not remembering it very well. My notes here and see if I know it's, nope, not really. Yeah, good question. I don't know if I have a good answer right now, and I don't want to pretend like I do. So I'm going to leave it there for now and say, I'll come back to that. I'm gonna think about this a little bit more and think about how I'm supposed to do that. And I'll say it later. Because I was like, oh yeah, I don't remember how to do that. I know it's a tough question. So let's look at one more recursively defined sequence. Also, I should point out, if you all have questions about things I am not talking about, that's totally fine. Like I can switch gears, but I feel like people are still talking about sequences. I know series are like right around the corner, but I feel like sequences are probably worth looking at. So let's look at one more. Let's look at the sequence. Here are the terms of the sequence: 2 plus 1/2, 2 plus 1 over 2 plus 1/2, 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, and on and on and on. Fun. Not really. It's not fun. It's fine though. It might not be fun, but it is fine. So someone might ask the question and say, before you do anything else, write this as a recursively defined sequence, which I think is maybe not the easiest thing to see. So it looks like if I look at, say, this term here, it looks like I took the previous term and put it in the denominator right there. So what, and that looks like it's true for every subsequent term, right? Each next term is 2 plus 1 over the previous term. So it looks like our recursively defined sequence is, I don't know why I decided to write recursively defined sequence, but I did. A sub n plus 1 is equal to 2 plus 1 over the previous term. I think that seems right. Oh, we have to pick a starting point too, right? Where a sub 1 is 2. That works. A sub 1 is 2. A sub 2 is 2 plus 1 over 2. Yeah, totally fine. Okay. So we're going to do this one. We're not going to do all the stuff for this one. We're just going to talk about how you would find what it could converge to, not the whole bounded and increasing or decreasing kind of thing. That's often more than you have to do. So what could this converge to? Well, here's something I probably should have said before, but didn't. It's fine. So if a sub n converges to some limit L, then so does a sub n plus 1, right? We're just saying take the limit meaning the limit as n goes to infinity of a sub n is equal to L is equal to the limit as n goes to infinity of a sub n plus 1. Right? It doesn't matter if you go one more term out, they're still going towards the same limit if that limit exists, which is always kind of the caveat that we're working under. Oh yeah, if limit exists, things work the way we want them to. If it doesn't exist, then so that just gets us back to the thing we did before, where we're going to say, well, this is going to converge to some limit L, and so is this, but so is this. So yeah, what we're going to do is we're going to take a sub n plus 1 equal to 2 plus 1 over a sub n, and then we're going to replace everything with just what a sub n plus 1 and a sub n are converging to. It feels kind of like, it almost feels like you're cheating. I'm not gonna lie. Like it always feels like, really, we can just do that? Yeah, we can totally just do that. And it totally works. But it kind of feels like you're doing things a little bit on the shady side here. That's okay. I'm gonna try and solve for L. I'm gonna multiply everything by L. So I'm gonna have L squared equal to 2L plus 1. Bring everything to the left. L squared minus 2L minus 1 equals 0. And I really wish it factored, but it doesn't. So I have to use the quadratic formula. So my L is going to be 2 plus or minus the square root of 4 minus, not 4, yeah, 4 minus, yep, sorry, minus 4 times 1 times negative 1 all over 2, which ends up being 2 over 2 is 1. Square root of 8 is 2 root 2 divided by 2 is just root 2. So 1 plus or minus root 2. All right. Which of those seems like the possible actual thing we're converging to? Is this converging to 1 plus root 2, or are we converging to 1 minus root 2? What's 1 minus root 2? I mean, I don't know exactly what it is, but I know it's not positive, right? This is a negative number. It certainly seems like all of our numbers are positive here. So this is not the limit. This is. So this does converge to 1 plus root 2. This is often how we deal with finding what a recursive sequence converges to. Question.
If like we were given our sequence of A's to determine like A1 or like A2, like you plug in like a number.
Right. And so I've been kind of, yeah. So, well, so typically if it's recursive, you have to be given the starting point. So we were given somewhere, yeah, right here, a sub 1 is 2. And so then if we wanted to, although we don't have to because it's already written out, we could start writing out more terms. So a sub 1 is 2, and then a sub 2 is 2 plus 1 over 2. And then a sub 3 is 2 plus 1 over that, and so on and so forth. Yeah, totally. Now, in this one, the terms were given because they told us, here's the terms of the sequence, and then figure out what the pattern is. Whereas in the previous problem, they didn't give us the terms. They just said, here's the recursive sequence, and here's your starting point. And then we wrote out a couple terms to kind of have an idea of what was going on. Cool. See, I'm just looking at this Casal's homework assignment to see if there's anything else that's really popping out to me that seems interesting. Yeah, it seems very interesting. I do like, I'm just going to address one question on here because I think it's worth mentioning. Question number 4 on this homework assignment, where he talks about this sequence is. That's an interesting one. So he wrote the sequence a sub n equal to n squared natural log of n, growth slower. I think he meant right, grows slower than, and then you've got the following one. So let me just ask, how would we check? I want to check whether I'm going to make something different up. A sub n equal to n times the natural log of n grows slower than. Let's make up something interesting. Sure, why not? That seems kind of boring. I'm going to go with natural log of n squared. Wow, that's really not focused. Okay, so if you want to see if something is the slower grower, it should be the thing. Well, here's what I would do. I would make a fraction, but the thing I want to be slower on top because I like my limits to be 0. So what I'm going to check is I'm going to check the limit as n goes to infinity of the proposed slower thing over the proposed faster thing, which may not actually be true, but that's the way I'm going to write it. Now, if the thing on top is the thing that grows more slowly, this limit should be 0. This limit should be 0 if natural log of n is quote unquote slower. Okay, well, let's check it out. I'm going to simplify before I start using L'Hopital's rule just all over the place. I can cancel a natural log of n. So this is really going to be the limit as n goes to infinity of n over the natural log of n, which we already know is not going to be 0 because we talked about before how natural log of n grows more slowly than n. But we can also show it, and we should, right? We probably shouldn't just say, yeah, I know it's infinity. We should use L'Hopital's rule because we have an infinity over infinity type of limit. So using L'Hopital's rule, the derivative of n is 1. The derivative of natural log of n is 1 over n. And then if I simplify this a little bit, I've just got the limit as n goes to infinity of n, which is for sure not 0. It is definitely infinity. What does this tell us? This tells us that actually the top thing, n natural log of n, grows faster than the bottom thing, natural log of n squared. So when you take a limit of a quotient like this, if the limit is 0, that means the top thing is the slower grower. If the limit is infinity, that means the top thing is the faster grower. And if the limit's some constant, then you don't really get to say one's faster than the other. questions about this? I didn't say much. What I said was, if the limit's a constant, you don't have a good, basically, what you're really saying is the limit's a constant, then they're always in proportion to each other. So it's not that one's really fast or slow, the other one, they're just one's kind of always a multiple of the other one. Ellie, do you have something? Okay. Yeah, we might as well say this into here. So it's good to have an idea of what things grow faster than other things. So I'm going to make a quick little list just to kind of show you. Typically, on the slow end, we have natural log. Natural log is typically kind of like the slowest thing you've got. You can make slower things by manipulating natural log, but if I'm just talking about like functions kind of without making them more complicated than just one kind of thing, natural log of n, or any log base 10, log base 2, log base whatever, is pretty much your slowest growing thing you've got. And then less slowly, but still slowly, are roots, like square roots, cube roots, whatever. Typically, I would say like the pth root of n, where p is a positive integer. So p could be 2, 3, 4, etc. So when I read this, I read, oh, roots are always going to outpace logarithms in a very similar way that exponential things outpace polynomials. So then the next thing kind of in the middle here is just good old n by itself. N to the first, right? Linear function. That I now like to put them in the middle. I know they're also polynomials, but like I like to clarify just because usually they kind of them. And then after that, n to a power, like n squared, n cubed, etc., where again, p is some positive integer. And then what outpaces polynomials are exponentials. So like e to the n, e to the n, 2 to the n. I typically like to write this as e to the n, where b is a base that is greater than 1. Right, because if you had like 1/2 to the n, it would actually end up getting smaller over time as n got bigger. And then after exponentials, what comes after exponentials? Factorials. Factorials are kind of the fastest thing. I think there's one more thing to consider that actually does grow faster, which comes up semi-often, is n to the n. N to the n actually outpaces the factorial. So how could you show any of these are true? Well, by taking the limit of either way. I usually like to do the slower one over the bigger one or the faster one because I like my limit to end up being 0, not to end up being infinity. But you could do either way. So if I wanted to actually show one of these, I could show, for example, I could show that, sure, let's pick a fun one. N cubed is slower than, say, 2 to the n by finding that the limit as n goes to infinity of the slower thing over the faster thing ends up being 0. That's how you show that one thing is slower than the other, by showing that if the limit of it on top over the other on the bottom is going to be 0. Or if you prefer, you could flip it and show that the limit was infinity. That would also be a totally legitimate way of doing it. And this one's easy to show it's going to be 0. We just apply L'Hopital's rule 3 times. So you do the limit as n goes to infinity of n cubed over 2 to the n. You do L'Hopital's rule once. Because it's infinity over infinity, you got 3n squared over the derivative of 2 to the n is 2 to the n times the natural log of 2. You do it again because you still have infinity over infinity. And you get 6n over 2 to the n times natural log of 2 times another natural log of 2. And finally, you do it one more time. And the derivative of 6n is 6, and the bottom is going to be 2 to the n times natural log of 2 to the third. That's going to go to 0 because the top is a constant, the bottom is getting infinitely large. So that shows that n cubed is a slower thing than 2 to the n. But more generally, right, n to any power is always going to grow more slowly than any exponential thing, as long as your base is greater than 1. So for that question there, for problem 4, for those of you in Casala's class, the way I would try to show that that sequence is slower than other ones is by doing it over the other one, taking the limit and seeing if I get 0 or not. Okay. So let's look at some series. So I said we would start talking about them. I know we only have like 7 minutes left, but we should start talking about series. So when someone says the word series, they really just mean we are adding up a bunch of terms. For some reason, it feels really easy to interchange the word series and sequence. Like they start with the same 2 letters. They're in the same section of the textbook. So just be careful. I might accidentally say sequence when I mean series. I will try to not do that. But when we say series, we just are thinking about adding up terms. Adding up terms of a sequence. Oh my gosh, calm down. I feel like I never even turned on Siri on my phone. What are you doing? Okay, that's terrible. Anyway, I said series. Okay. So let's look at this infinite series. The sum from n equals 1 to infinity of 2n over n plus 1. So I'm going to start writing out terms. I've got, let's see, n equals 1. I've got 2 over 2 plus 4 over 3 plus 6 over 4 plus 8 over 5. And we just keep going forever and ever and ever. Plus, let's say, 200 over 101. The question we're often going to be asking is, does this series converge or diverge? Well, it looks like I'm adding up a bunch of numbers, literally an infinite number of numbers. And at least when we go further out here, all these numbers are getting really, really close to what? Like, what's 200 over 101 basically equal to? 2. And the next one's also just about 2, but we're adding up 2 a lot, like an infinite number of times. So what it looks like we're doing here is we're essentially adding up 2 an infinite number of times. Well, 2 plus 2 plus 2 plus 2 plus 2, an infinite number of times is going to add up to infinity. Or you could say 2 times infinity if you really wanted to, but that seems silly. So this is going to be infinity. This series diverges specifically to infinity, but there's something important to see here. And that is, we knew that the limit as n goes to infinity of the sequence was 2. And that's how we were able to really kind of say, well, look, we know that our terms are getting closer and closer to 2, so we're just adding up things that are essentially like 2, that an infinite number of times. Well, if you're adding up any non-zero finite number an infinite number of times, you're going to get infinity. It could have been 2, it could have been 1/1000th. You add up 1/1000th an infinite number of times, you're still going to get infinitely large. So the takeaway here is that if you know that this limit of the sequence is anything that's not 0 and finite, or I guess it could be infinite, but specifically not 0, that this series is going to have to diverge because you're just going to add it to infinity. This is going to mean, which means our series must diverge. And this actually kind of leads to the first of many tests about whether a series is convergent or divergent. We're going to write that, and we're probably going to do them. So this is called either, I really do prefer, so there's 2 names for this test. I think you should call it the first name, which is the test for divergence of a series. And the reason it's good to call it that is because then it reminds you that you can only ever use this test to show that a series diverges. You can never use the test for divergence to show the series converges. It doesn't work. So if you ever find yourself writing the series converges by the test for divergence, take a step back. Oh wait, that's not it. The other name for this test, which is less kind of indicative of that is the nth term test. And what this test says is that in the series, so in the series of a sub n from n equals 1 to infinity, or you really can start wherever, if the sequence has a limit that is not 0, then the series must diverge. So if the sequence converges to something that is not 0, then the series has to diverge. I should really actually say that's actually I'm being a little not general enough there. I should have really said if the sequence doesn't converge to 0, then the series diverges. So you could have a sequence that is divergent. That will also mean the series of a sequence diverges. So another example of this would be something like the sum from n equals 1 to infinity of 5n squared over 2n plus 1. The terms of that sequence definitely don't go to 0. The limit as n goes to infinity of 5n squared over 2n plus 1. What is that limit? It's not 5 halves. It is infinity because the top power is higher than the bottom, or I should say the top degree is higher than the bottom degree. But that's definitely not 0. So this series must diverge. Okay, last thing I want to say, because I don't want you to walk away with a misconception here. Here are two series that are very probably the series we use often to talk about convergence and divergence. So this series, the sum from n equals 1 to infinity of 1 over n, is a divergent series. We'll talk more about how to show that next time. It is called the harmonic series, but I want to point out the limit of its sequence is 0. The limit as n goes to infinity of 1 over n is for sure 0. So the limit of the sequence being 0 does not guarantee convergence or divergence. It just means you have to do more work. On the other hand, as a contrast, this series from n equals 1 to infinity of 1 over n squared converges. And just to say all the things, the limit of its sequence is also 0. So if the sequence converges to 0, the series can do anything. It could converge or it could diverge. If the sequence doesn't converge to 0, then you automatically get to say that the series diverges. Cool. All right.